everybody. We're back. My hair looks funny, sorry. Um, we're back and the part one of this video explained how oxygen gets carried by hemoglobin and diffuses across membranes, either to get into the tissues or get from the lungs into our bloodstream. And we talked about how it binds to hemoglobin and we looked at oxyhemoglobin curves. Now we want to look at carbon dioxide. What happens with carbon dioxide in our bloodstream? How do we carry carbon dioxide? So this is a picture of a blood vessel. You can see the yellow is plasma. And so over on the left side here, let me turn on my laser pointer so you can see what I'm pointing at. We're on the left side here. This represents our tissues. And so this would be a capillary over at our tissues. You can see that oxygen has dissociated from hemoglobin because the partial pressure gradient is lower on this side than it is on this side. So that favors the dissociation of oxygen from hemoglobin, and oxygen moves into the tissues. Now we have unbound hemoglobin here. Okay. But we also notice that the tissues have built up CO2. And so because of the partial pressure gradient, it's about 46 for CO2 at the tissues and about 40 at the plasma. And so CO2 is going to move into the bloodstream to be carried away. Okay, and so the way the blood carries CO2, carbon dioxide, is in 3 different ways. So one, it can be dissolved, just CO2 dissolved right into the plasma. Some of it will enter and just simple diffusion cross into the red blood cell and just be dissolved in the cytoplasm of the red blood cell. Okay, some of it can actually bind to hemoglobin. So you can see that once oxygen dissociates from hemoglobin, we've got a pathway here for it to bind. Okay, and so we do have what's called carboxyhemoglobin. Carboxyhemoglobin. That means hemoglobin is bound to carbon dioxide. Okay, but the most common pathway is for CO2. Once it enters the red blood cell, it will react with water and with the help of an enzyme called carbonic anhydrase. See that down here at the bottom, carbonic anhydrase. That will facilitate the chemical reaction between carbon dioxide and water, and it will make carbonic acid, which will dissociate. It will release a hydrogen, and that hydrogen can bind to hemoglobin, and the hemoglobin will carry it. And then this HCO3 negative, because it released the hydrogen with that, so it took the electron from that hydrogen, so it's negative. That's now called a bicarbonate ion. And it will, through facilitated diffusion, it will diffuse out of the red blood cell into the plasma. But because we have a negative ion entering the plasma, we're going to pull a negative ion out of the plasma. That keeps the electricity in balance. Remember, the polarity in balance. We don't want to shift the polarity. So we do that. We balance it by pulling in a negative chloride ion. This is called the chloride shift. The chloride shift. So let me walk you through this chemical equation here. I went through that a little bit fast, but let me use the whiteboard here in order to show that chemical equation again. Before I do that, I did want to just go. So you saw this table before. We looked at how oxygen is carried in the blood, but now let's look at how CO2. So I said it can be physically dissolved either in the plasma or the cytoplasm of the red blood cell, but only about 10% of it is carried that way. Some of it can, once it enters the red blood cell, it can actually bind to the hemoglobin, and it doesn't bind to the heme group. It actually binds to one of the protein subunits. And when it does that, that's another reason that the partial pressure of oxygen or CO2 can affect oxygen. When it binds to the hemoglobin again changes its shape a little bit and it pops off more oxygen. But only about 30% does that. 60% of hemoglobin travels through our bloodstream as a bicarbonate ion. So again, let me go back and let me work on this chemical equation for you. So I need to, I just lost my laser. There it is. I need to get rid of my laser, and I'm going to stop sharing here, and I'm going to go to my trusty iPad, and I'm going to share the whiteboard. There it is. All right, there it is. So again, 60% of CO2 travels in blood plasma, got the L, as bicarbonate ion. Okay, and bicarbonate ion is HCO3 negative. Okay, how do we get that? So again, just imagine we're inside of the red blood cell. I'm not going to draw that. Okay, we're inside of there, but CO2 enters. And remember, just like any cell, most of the cytoplasm, the fluid that's in there, the intracellular fluid, is water. H2O. It's water. And so what that does is there is an enzyme inside of the red blood cell, and that's carbonic acid, Ca. Okay, and so I'll write that down here. Ca equals, I said carbonic acid, carbonic anhydrase. Carbonic anhydrase. Okay, and look at that. ASE. Remember, ASE means enzyme. So this is the enzyme driving this reaction. Okay. Now, remember, this reaction would happen anyway, but the enzyme helps to speed it up. Okay, so the enzyme speeds it up. So what happens is, and I'm gonna write a step in here that the PowerPoint didn't show you, but it helps you to understand it a little bit better. And actually, I'm pretty sure in the red blood cell, it does skip this step, but I'm going to draw it for you because it's going to help you just kind of in your chemistry see how things are being put together. Because remember, in chemistry, it's almost like an addition problem, right? These two things are going to combine in such a way that they have to balance each other out. So if I have two hydrogens, I'm going to stay with two hydrogens once they react. But I have two oxygens in the carbon dioxide and one oxygen in the water, I should end up with 3 oxygens, and I do. So what happens is you first get H2CO3, right? I have 2 hydrogens, right? I have 1 carbon dioxide and I have 3 oxygens. This is carbonic acid. But what happens is that dissociates. And I think the carbonic anhydrase helps it dissociate. So that's why it skipped that step in that red blood cell. So what do I mean by dissociate? One of these hydrogens, right, breaks off, and it does. It comes off as H, and it leaves an electron behind, H plus. So what does that leave me with? That leaves me with 1 more hydrogen, the carbon, and the 3 oxygens. But since the hydrogen, right, is positive, and I'm going to erase that because it looks funny, right? But since it's positive, that means it left an electron somewhere. It did. It left it here. Whoops, I got to put my pen back on. It left it here. So this is bicarbonate. Now the bicarbonate is going to come out. So if this is the end of my red blood cell, and I've got a nice little transporter here, bicarbonate is going to shift out into the plasma, right? But if all of these negative ions came out into the plasma, that would change the polarity from the inside of the cell, right, to the outside of the cell. We don't want to do that. Well, your plasma also carries chloride. So to balance a negative ion leaving the red blood cell, chloride is going to move in to the red blood cell, and that's called the chloride shift. Okay. I'm going to call that right here the chloride shift. So now your blood is coursing around with all this bicarbonate inside of it. Okay, and so remember that our blood has to maintain its pH. Okay, and so the pH of blood can't be too acidic. So the pH of blood is usually around 7.2, right? 7.2. And so what happens is if other processes are going on where hydrogen is being released, remember more hydrogen ions lowers the pH value. So we can get 7 is neutral. That's really acidic for us. It doesn't work for us. Our blood can't be that way. We don't want it to go much lower, right? Actually, I think our blood pH, there's a range, 7.2 to 7.4 is the range. And so if more hydrogens start to build up, then our blood pH would go below 7.2 and it could go to 6.9, 6.8. That wouldn't be good, but it doesn't because this hydrogen can get bound by this bicarbonate, and that is what neutralizes our blood. Okay, or puts the pH back to what we consider to be normal. We're a little bit on the basic side. All righty, so that helps, that happens there. The other thing that can occur inside of the blood, I'm going to erase this for a minute, that can occur inside of the blood cell is because now when we release this bicarbonate ion and it goes out, look, we're left with this, and now the blood, we're left with that hydrogen ion. Now the blood could become acidic. So it doesn't do that though, because the other thing we said that hemoglobin can attach to carbon dioxide. Well, it can also attach and carry the hydrogens. And so by carrying the hydrogens, it prevents the red blood cell from getting too acidic. Okay, so this is how we convert CO2 back into, or we convert carbon dioxide into bicarbonate. And it's a way that we can carry a lot of carbon dioxide and carry it through our blood. But then the bicarbonate acts as a buffer. So this system is actually very important, again, as a way to keep our blood within that homeostatic level of acidity. Okay, and so that is what I just showed you down here at the tissues. Okay, but then as the blood is moving around and then heading back to the right side of the heart to the pulmonary circuit, we want to get rid of this CO2. And so we do. Everything you see here happens in reverse. So because of the pressure gradient, remember it's low inside of the lungs compared to here, the partial pressure of CO2 is about 46, and it's about 40 in the alveoli. So the dissolved CO2 comes out and goes into the alveoli. The dissolved CO2 in the red blood cell will diffuse across membranes back into the alveoli. The hemoglobin that was carrying the hydrogen will go back. So the bicarbonate in the blood by the chloride shift will come back into the red blood cell. That means the chloride will go out. And then taking that hydrogen from the hemoglobin, this bicarbonate will bind to it. And the same enzyme, carbon dioxide, will run this in reverse, converting it back to CO2 and water. CO2 will diffuse out because of the partial pressure gradient. Okay, and then also because of the partial pressure gradient, there's a higher affinity for hemoglobin to oxygen, so it will release any of the CO2 and it will dissolve out, right? And then starts all over again when we get to the tissues. So I want to make sure that you know that chemical equation. You need to be able to work out that chemical equation down here of how to convert carbon dioxide into bicarbonate. And why do we do that? What's the reason that we convert carbon dioxide into bicarbonate? What's the homeostatic reason for that? Okay, and then make sure you can tell me the other ways that we can carry CO2 in the blood. Okay, and this table helps you with that. And then also how we carry oxygen. Okay, so what are some of the problems we can get, abnormalities in our arteries with the partial pressure of oxygen? Well, if we're not carrying enough oxygen at the cell level, then we have a condition called hypoxia. Hypoxia. Remember, hypo means low. So this is low, low oxygen levels. Right? There's different types of hypoxia. Hypoxic hypoxia. That is, we just have low oxygen in the cells. Anemic hypoxia, hypoxic hypoxia, I should say, is because we don't have oxygen available to us, right? Anemic hypoxia usually has to do with the hemoglobin, if we don't have enough hemoglobin to bind to it. Circulatory hypoxia, something's going on that it's not able to pick up enough oxygen or carry enough oxygen, I should say. And you know what, I'm not even going to ask you specifically what each one of these things are. So I think if you're interested in them, then you might, if you want to look more into them, you can. I do want you to know what hypoxia is. So that's that first bullet, condition of having insufficient oxygen at the cellular level. And then, but what is hyperoxia? So hyperoxia could have a condition of having above normal atrial partial pressure of oxygen. Okay, so you have too much oxygen in your blood. Usually this only occurs if the person is on supplemental oxygen. This is one reason if you're a diver, you have to be careful at going too deep and staying too long at certain depths because the pressure is higher. When the pressure is higher, you can absorb more oxygen into your tissues. And so it could be dangerous. And it's also dangerous if you put a patient on supplemental oxygen and you don't watch them carefully as how much oxygen they're getting. And the reason is because the way our body responds to breathing rates is one of the things it does is it can look at the level of oxygen in our blood. And so I'll explain this a little bit in just a little bit on another slide, but just real quickly, we have chemoreceptors that are specific to the level of partial pressure of oxygen. And so when the partial pressure of oxygen gets high, the chemoreceptor senses that and sends a signal to the brain, and the brain decides, oh, we have enough oxygen, so it will slow down the breathing rate. Okay, and so if you give someone too much supplemental oxygen, then the brain will continue to ramp down breathing, ventilation breathing, to the point where the person can actually just stop breathing. The brain will stop the breathing from occurring. So that doesn't normally happen in everyday life. But if somebody is breathing oxygen from a tank, that's what could happen to them. So you have to be very careful with that, especially in medical facilities when you put someone on supplemental oxygen. Okay. There could be abnormalities with the partial pressure of CO2 in our arteries. So again, just kind of know what these mean. So hypercapnia is when you have too much CO2 in the blood. And that can happen by hypoventilation. So remember that we release CO2 by exhaling. So if someone isn't breathing normally, their breathing rate has slowed down a lot, that means so has the exhalation. So they're not getting rid of that CO2, but our cells keep making CO2, so the blood keeps picking it up. So that can cause too much CO2 in the blood. Normally, that will trigger, we also have chemoreceptors for CO2, and that will trigger the sensory response up in the brain, will detect it, and then cause you to breathe more rapidly. And so to get rid of that CO2, or at least do more deep breathing. And so because with the deeper inhalation, you have a deeper exhalation too, and you end up breathing out more CO2. And that's really what our body is more sensitive to. It's actually more sensitive to the level of CO2 in our blood, and will more quickly adjust the breathing rate to the level of CO2 in the blood. So that's one of the main reasons why when you're working out, you're doing some kind of athletic activity, that you get out of breath. We always think it's because we're trying to resupply our body with oxygen. Well, you just saw how much oxygen the hemoglobin carries, and we don't use most of it at rest. So we have a lot of extra oxygen, plus your muscles have a pigment molecule called myoglobin. So very similar to hemoglobin, your skeletal muscles have the ability to store oxygen inside of there. So we first get to a point where we actually have too much CO2 in the blood, and that's what increases the ventilation rate, because the idea is to blow the CO2 out. Okay. So hypocapnia is usually when there's below normal arterial partial pressure of CO2 levels. Okay, and this can come on by hyperventilation. Okay, so you always see in the TV shows or in the movies, somebody's panicking and they start to hyperventilate like this, and somebody hands them a paper bag and tells them to breathe in the paper bag. Okay, so again, what's happening is when the CO2 levels are going down because they're panicking and you're not breathing deeply enough. And so again, if you don't breathe deep enough, that means you're not exhaling a lot. So if your exhale is shallow, then I'm sorry, I'm just saying that. I just said that backwards. So if you're hyperventilating and you're breathing off too much CO2, right, then you have below normal arterial levels. So what you're doing by breathing in the bag is when you exhale, you're exhaling CO2, but the bag is catching it. So the next inhale has a higher proportion of CO2. So the pressure gradient's changing. So you're actually putting CO2 back into your lungs or back into the blood. Okay, so that's the anxiety states. So I hope I didn't confuse you. So I'll say it again. Hypocapnia, below normal CO2 levels in the blood. And that can happen when you hyperventilate, like when you're anxious. So you're hyperventilating and you're breathing out too much CO2 more quickly than what you should be doing. So the blood levels of CO2 is getting too low. Okay, so breathe into a bag. So that means you exhale the CO2, the bag captures it. So the next inhalation has more CO2. So you can put it back into the bloodstream. And then you'll see the person start to calm down. Okay, fever can cause that. Aspirin poisoning can cause that. So again, those are conditions of hypocapnia. Okay, and so how do we control the respiration? We looked at the brain and the function of the brain. We saw we were down in the brain stem here, and we have the respiratory control centers in the brain. So it starts down in the medulla oblongata. Remember, we have the medullary respiratory center there. We actually have areas where, again, it's a cluster of cell bodies of neurons, a dorsal respiratory group and a ventral respiratory group. And these are different cell bodies, groups of cell bodies that control inhalation and exhalation. Mostly it's the inhalation that is firing, because most of, so the inhalation is causing the triggering of the phrenic nerve and other nerves to control the diaphragm and the external intercostals. But remember, at rest, exhalation is just a relaxation. So I believe it's the ventral respiratory group controls the neurons that control the other intercostal muscle or internal intercostal muscles and the the abdominal rectus abdominis groups to help do forceful exhalation, right? So the other group is for forceful exhalation. And then we can modify our respiration rate by these two groups in the pons. If you remember that the pons has respiratory centers. So we have the pneumotaxic center and we have the apneustic center. And the apneustic center can stimulate the inhalation cells of the medulla to develop more deep inhalation. And then the pneumotaxic can inhibit the apneustic from stimulating the medullary center. That kind of slows respiration rate. Okay, so apneustic prevents the inspiratory neurons from being switched off and gives an extra boost to the dry, whereas the pneumotaxic can inhibit that from occurring. Okay, and then we have something, and I'm not going to worry too much about this semester, something called the Herring-Brewer reflex that just triggers to prevent overinflation of your lungs. So just suffices to say our brain has that control to it. And then the chemical factors that play a role in determining the magnitude of ventilation is what we kind of talked about before. The partial pressure of oxygen, the partial pressure of CO2. Remember that when there's too much CO2 in the blood, then that can release more hydrogen ions. So that can change the acidity of the blood. So that's also being detected. And just a moment ago, I'm not sure if I said this right, but so I want to be clear that yes, the dorsal respiratory group has mostly inspiratory neurons for inhalation, right? And the ventral respiratory group has both inspiratory and expiratory neurons. Okay, so the dorsal group is only inspiratory. All righty, and so these are those chemical factors that affect respiration. So this is what I had been talking about looking at the previous slide. So it's all summed up for you in the table. So when the partial pressure hypoxia, partial pressure of CO2 goes low, right? That you have these chemoreceptors in the peripheral, in the arteries and things like that. And so they're only stimulated when the partial pressure of CO2 falls below 60, right? And that's again at the arteries, not down at the tissues. So that's considered an emergency situation. You also have chemoreceptors, central chemoreceptors, those are in the brain, right? And so you can see that it's mainly the peripheral chemoreceptors that really get triggered, that are primary when the blood oxygen gets too low. Okay. Here in the CO2, partial pressure of CO2 in the atrial blood, if the peripheral chemoreceptors detect that, it's pretty weak, that a change in respiration changes, because I mean, your tissues all over your body is releasing a lot of CO2 all the time. But in the brain, in the central chemoreceptors, that can be a dangerous situation in the brain, because again, too much CO2 can change the pH too quickly. And so that's what's written here. So if the amount of hydrogen goes up, remember that means the pH goes down. That means it's more acidic, right? And so that could do damage to the brain really quickly. So we stimulate the respiratory center right away to help deal with that situation. Okay, and then if it's just, it's not about the partial pressure of CO2, but it's just the acidity in the blood, right? Then we get more of the effect of the peripheral chemoreceptors, okay, because that is more right at the tissues. All righty. And so where are some of these receptors? We've got the peripheral chemoreceptors. We saw, I think I talked about this a little bit before too. We've got in our carotid bodies, remember up in the carotid arteries that head up to our brain, these are the carotid bodies, these kind of swelling that occurs here. And that's where we have those chemoreceptors. And then remember, every receptor is attached to a sensory nerve. So that's heading up to the medulla oblongata. And then right at the aorta, there are aortic bodies, also chemoreceptors. So it makes sense, right? So the amount of oxygen and CO2 in our brain is really important to regulate that. So we have carotid or chemoreceptors in the carotid arteries. That's what brings the blood right up to the brain. So test the blood right away. Okay. And then as blood is leaving the left side of the heart, let's just monitor it right at the aortic arch, right before it starts to go to the rest of the body. So again, we adjust the breathing rate accordingly because we test it right away as the blood is just heading to the systemic system. All righty, so that's it. Thanks, guys. That's it for Unit 3. So this is the last lecture in Unit 3. Thanks for listening. Hope you enjoyed it.